Hello and welcome to part 2 of our chapter 11 inference about a mean. We're going to pick up where we left off and we're going to start talking about confidence intervals for mu. So just like we did confidence intervals in the last chapter, we would do basically the same thing when we were doing confidence intervals for mu and x bar with our t-tests. So we have a typical point estimate plus or minus the margin of error. This is the formula we use. So remember that since we're changing our standard deviation from a known population to the sample population, we're using S as our standard deviation. And since we're using that, we're using a t-table. We're going to start using the t-table information to find our confidence intervals. And that's denoted by t subscript n minus 1, which are degrees of freedom, comma 1 minus alpha over 2, which sets our 1 minus alpha confidence interval. Similar to the z-procedures, except uses S instead of sigma, and similar to z-procedures, except uses t instead of a z-score. So when we switch around, this is our alternative formula, our x bar plus or minus t to the 1 minus 100 degrees of freedom and 1 minus alpha over 2 times the standard error over x, where the standard error over x, remember, is S over the square root of n. So confidence interval example, we're going to calculate 95% confidence interval for mu for the birth weight of the SIDS babies. So we had our x bar as 2,890.5, our standard deviation is 720, and our n equals 10. So we calculate a 95% confidence interval for mu. So for this one, we're going to go to the back of the book and we're going to find our C table, which is going to be our t-distribution table. And if we look up our t-distribution of 10 minus 1, so we're at 9 degrees freedom, which you can find on page 546, and we want a confidence interval of 95, when you go over and look at degrees of freedom of 10 minus 1 and a confidence interval of 95, not a confidence interval for 95, but remember we're doing a two-tailed t-test, so it's 0.05 divided by 2, so you're actually looking at the confidence interval of cumulative probability, remember, because it's two t-tailed tests. So it's 5%, but it's divided by 2 for both sides, so it's 2.5 on each side, so the cumulative probability from that point over is 0.975, so degrees of freedom and 975, and it will give you your 2.262, which is what we have right here. So we have our 2,890.5 plus or minus 2.262 times our standard error. When we work this all out, we're going to get a confidence interval of 2375.4 to 3405.6 grams. So that would be our confidence interval, and that's how you calculate it. A second example is we have our percents of ideal body weight in 18 diabetics, and here we have a data set. Based on these data, we want to calculate 95% confidence interval for mu. So what you do is we have to actually take the data set and calculate it out. Luckily for you, this is already done, but if you did take this all out and calculate our average and get our x bar, we'll get 112.778, and then you'll get a standard deviation. Remember, when you use the standard deviation here, you're going to go and do the normal standard deviation, but make sure you're doing n minus 1 in this equation, and then you have an n equals 18. So our standard error is the standard deviation over the square root of n, which will give us 3.4. In this one, we're going to go look in the back, and since we want a 95% confidence interval, remember, since it's going to be a two-tailed test, so we're going to do our n minus 1 for degrees of freedom, so 18 minus 1 is 17, so you go to the back of the book, you find degrees of freedom 17. We're finding our t-distribution of 0.05 on two tails, so it's a cumulative probability of 0.975. When you go over and find that, you'll find it's 2.110 from the table. Plug all these numbers into our equation to get our confidence interval, and we come up with a confidence interval of 105.6 to 120.0. So now we're going to talk about paired samples. So previously we were talking about confidence intervals and single t-test. Now we're going to go to paired samples. Paired samples is each point in one sample is matched to a unique point in the other sample. Pairs can be achieved via sequential samples within individuals, as in like pre-post tests, crossover trials, and match procedures. So pre-post tests would be something that's measured before and after an intervention in the same set of individuals. Crossover trial is which starts one treatment and then switches to a different treatment, so they cross over and treat different ones. Match pair is when subjects in one sample are matched to subjects in a separate sample based on specific criteria. Or also we can call them dependent samples. So match pair or dependent samples, either one are applicable. So an example of match pair, so in this one the book talks about whether oat bran can reduce LDL cholesterol with a crossover design. So subjects with crossover design from cornflake diet to an oat bran diet. So half the subjects start on a cornflake and then the other half are on oat bran. 2 weeks on diet 1, they measured their LDL cholesterol. They have a washout period. Then they're going to switch the diets. 2 weeks into the second diet, they measured the LDL cholesterol. So here's our example data where we have subjects 1 through 12 here, and what their LDL cholesterol was on the cornflake diet, and then what their cholesterol was on the oat bran diet. What we're going to do is what we're going to call now calculating the variable delta. So now we have a new variable delta. Delta, so you may have seen before in chemistry, is the change or the difference between the two. So the way we calculate delta is we're going to take the cornflake minus the oat bran. Just note the order of subtraction doesn't materially affect the results, but does change the sign of differences. Here are the first 3 observations. So if you take your cornflake minus your oat bran, you get your delta for each one. And here we just denote positive values represent a lower LDL on the oat bran. When you actually here are all the 12 paired data points for the deltas shown here. Here's our little stem plot. Remember these little guys from way back in chapter 3, and here's your box plot of it. So if you actually look at this box plot, you see here's our average, here's our quartile range, and our spread, right? So you can see if we go from here, it's going to be a negative skew, right? As we start here, it's going to kind of go like that. It's going to mound up. So we're going to have this somewhat of a negative skew, meaning about 0.45, results varying from negative 0.4 to 0.8. So that's great. We have these delta things. What else can we get from it? Well, with the deltas, we can actually calculate a lot more with it. Notice anytime you see the subscript D, that will be used to denote the statistics for a difference in variable delta. So for our delta here and our descriptive statistics that n equals 12, our x bar subscript D, remember, so our average delta variable would be 0.3808, and our standard deviation for delta is 0.4335. So now, if we wanted to calculate a confidence interval for mu delta, a T procedure directed towards the delta variable calculates the confidence interval for the mean difference. So we set our problem just like we have been for confidence intervals. We just have to make sure we go to the back of the book and find our new value for our T distribution. So our T distribution for degrees of freedom is 1 minus alpha over 2. If we go to the back of the book and look at that, so we had 12 samples there, and we do take our degrees of freedom, so 12 minus 1 is 11. Go to the back of the, not back of the book, but table C. And when you go to table C, you go to your degrees of freedom 11. And when you go over to find the cumulative probability, since we're doing 2 tails, it's 0.975. And you find the value of 2.201 from table C. Plug that in, times our standard error, which is our standard deviation of delta divided by our n square root. Plug that all in, and we get our confidence interval of 0.1052 to 0.656. Once again, that was the confidence interval delta. Back to our paired t-test. So to one sample, it's similar to one sample t-test like we said, but usually we set our mu0 or our null hypothesis to 0, representing no mean difference. So mu actually equals 0, test statistic. Our equation set up just the same as we've gone over, and when we plug in our example from our OPRAN data, we have our hypothesis, our null hypothesis stating no difference actually equals 0 on a paired t-test, and our alternative hypothesis not equal 0. So our t-test will be set up to our average x-bar of delta minus our mu hypothesis of 0.3803 minus 0, divided by our standard error, which would be our 0.4335 divided by the square root of 12 equals 3.0343. So now, and then our degrees of freedom once again is 11. If you go back to the back of the book and look this up, you'll get a p-value of 0.011. This is via the computer. The evidence against the HO is statistically significant, right? Because we have a p-value of 0.01. It's statistically significant at the alpha level of 0.05, but is not significant at alpha level of 0.01, right? So this is actually above 1%, just above 1%, but it is not significant at 0.01%, but it is significant at 0.05%. When they stated here that they did a via computer output, this is what a SPSS output of OPRAN data looks like. So when we get into actually doing SPSS and seeing the charts that they put out, this is what you will see. They'll give you the one sample statistics, which you can't calculate by hand, and that we showed, and then you'll get your one sample t-test. And as you look at the difference, you'll see the t-score, the degrees of freedom, the significance of two tails, the p-value, the mean difference, and the lower and upper confidence levels at 95%, which is everything we want to calculate, and they just give it to you in this nice little chart right here. Now moving on to conditions for inference. So t-procedures require these conditions. They require a simple random sample, individual observations, or deltas. They need to have valid information, no information bias, and a normal population or large samples, which will be part of the central limit theorem. These are the conditions for inference. So remember, as we're making inferences from the sample that we're collecting back to the population. That's what we mean by inferential statistics, when we take sample data and we're referring it back to the population as our results. This is what inferential statistics is applying, right? We don't know what the population standard deviation is, or a lot of even the data from the population, but from our sample we can infer back to them. So the normality condition. So the normality condition applies to sampling distributions of the mean, not the population, right? We're not looking at the population, we're looking at our sample. Therefore, it's okay to use t-procedures when the population is normal, the population is not normal, but is symmetrical, and the n is at least between 5 to 10 participants, right? So our n at least 5 to 10 people, and the population is skewed, and the n is at least 30 to 100. So if the population we're looking at is under 30 and it is skewed, we probably wouldn't want to use a t-test for that. We really want it to be somewhat of a normal distribution, or if it is skewed, it needs to be at least skewed with a high enough number of people in the study. So a couple examples of this would be, so this data set here, data set A, is skewed and small. So as we can look at the shape of it from the stem and leaf plot here, you can see it's skewed and it only has 6 people in the study. Therefore, we would want to avoid the t-test procedures. Dataset B has a mild skew and is moderate size, so we're going to use t-test procedures. So as you can see, it's somewhat of a mild skew, but it's somewhat reflecting maybe a bell curve, maybe if you had more samples, but our n is 25, and since it's not too much of a skew, we can use t-test procedures. Data C is highly skewed and is small, so we're going to avoid the t-test procedures in this one, right? We have n equals 13, which would be a relatively good size, but however, it is significantly skewed, and there's not much we can do, so we wouldn't want to use a t-test procedure for this type of data. Okay, the next slide is going to be going over sample size and power. Once again, it's something that we're going to go over. However, we won't. You won't be required to know this for any of the tests. So after I do this, I will help you through the one of the problems towards the end of the chapter for the exercise problems. There's an exercise problem on power, and I will help walk through that after I go over this examples of the slides. Alright, I'll see you all in the next video.